Spotlight today is on the final learning targets of this unit, 9, 10, 11, 12, and 13. 11 through 13 are repeats of what we've done before about determining order, describing the transformations, and performing them. Learning targets 9 and 10 focus on the basic properties in the graph of the tangent function. So today we're going to learn how to graph the final two of our 6 basic trig functions, tangent and cotangent. Before we actually start off graphing, I want us to think about a few significant places for tangent on the unit circle. So you'll notice that I have lined up tangent of 0 all the way up to tangent of 7 pi over 4. So I have all the pi over 4 angles, the 45-degree angles, and all of the quadrantals, 0, pi over 2, pi, and 3 pi over 2. The quadrantals are already labeled for you on this grid with their coordinate points from the unit circle. If you recall, tangent is sine over cosine. So if we use that quotient identity and our basic values, which went cosine, sine, we can come up rather quickly with the tangent value at each one of those quadrantals. So tangent of 0 would have been 0 over 1, which gets you 0. Tangent of pi over 2. Tangent of pi over 2 would be 1 over 0, which is undefined, which we have seen enough times to hopefully recognize that that is going to be an asymptote on our graph. Tangent of pi would be 0 over negative 1, which is going to get us 0 yet again. And tangent of 3 pi over 2 would be negative 1 over 0, which again is undefined. Now the pi over 4 angles are significant to us in our unit circle for tangent because tangent of pi over 4 in those 45-degree angles, you're going to have your sides 1, 1, and square root of 2. Opposite over adjacent, 1 over 1 is going to get you a 1. In the first quadrant, where tangent is positive, in the A quadrant, second, third, and fourth, those values are all going to be 1. It's just a matter of is it positive or negative. So in the second quadrant, in the sine quadrant, you have a negative 1. In the tangent quadrant, again, tangent is positive 1. And in the final quadrant, tangent is negative 1 again. We're going to use these values to help us sketch a graph of tangent on that next page. You should be looking at that graph right now, actually. So tangent of 0 is 0. So we're going to start off with that point. Tangent of pi over 4. Well, I don't have pi over 4 on my graph, but I'm in units of pi over 2. Pi over 4 would be half that distance. Tangent of pi over 4 is 1. Tangent of pi over 2 is undefined. That's going to be an asymptote on our graph. So sketch in your asymptote. Tangent of 3 pi over 2 was, or 3 pi over 4 was negative 1. Tangent of pi was 0. And tangent of 5 pi over 4 was 1 again. Then tangent of 3 pi over 2 was undefined. Another asymptote. Tangent of 2 pi would be the same as tangent of 0, and tangent of 7 pi over 4 was negative 1 again. If I kind of connect these dots, I really only have one full period, but if I connect these dots, those asymptotes, my function will approach as it goes to positive or negative infinity for the range. So I'm going to repeat this process throughout my whole graph to come up with this tangent function. It should be repeated with the asymptotes every pi, starting at that pi over 2 interval. So asymptote every pi. It should have a 0 in between each one. And it should be going up to 1 or down to negative 1 on either side. So to fill my graph, I'll have 3 full intervals and 2 extra half intervals filled in. Okay, so now that we know what it looks like, let's talk about its properties. General equation we just talked about is tangent of x. The domain of tangent of x is a little complicated because you have asymptotes almost everywhere you go. So this is a case where we're going to use our words instead of speaking in interval notation. Our domain excludes all of those intervals of the pi over 2's, okay? So we're going to say it's all real numbers except k pi over 2. Well, here's where this k comes in. K is a constant. It's at 1 pi over 2, at 3 pi over 2. The next one would be at 5 pi over 2, negative 1 pi over 2, negative 3 pi over 2, negative 5 pi over 2. It's all the odd integers. So it's all for the odd integers that are the value. So the 1, 3, 5, 7, etc. Our range, bottom to top, I've got everything covered in that graph. So negative infinity to infinity. We can go back to interval notation. Is it continuous on its domain? So from left to right, can I draw it down in one pencil stroke? Certainly not. No. What type of discontinuity do we have? Hopefully you remember this from a while back, Unit 7. This is infinite discontinuity. It is symmetric with respect to the origin. It is odd. If you rotate your paper 180 degrees by turning it upside down, it should look exactly the same. Minimum and maximum values, there should be none because you're approaching positive and negative infinity. But there are plenty of vertical asymptotes, and they happen at all of the places that were accepted from our domain. So they're all at x equals k pi over 2 for odd integers k. Okay. The period of the function, period, means the amount of time before it repeats. Okay. We see here we've got 3 and 2 extra halves here. How long did it take before it started repeating? Well, from negative pi over 2 to positive pi over 2, that's a length of pi. So the period of the function tangent is pi, which is different from the other graphs we've been looking at so far this unit. We're going to repeat this process for cotangent as well. This should go a little bit faster because we just did this for tangent. Again, we're going to think about cotangents, quotient identity. Cotangent of x is cosine over sine. We have all of our quadrantals labeled. Cosine over sine, 1 over 0 is going to get us undefined. Cosine at pi over 2 will be 0 over 1, which is 0. Cosine at pi will be negative 1 over 0, which is undefined. Cosine at 3 pi over, or cotangent at 3 pi over 2 will be 0 over negative 1, which is 0 again. Cotangent of pi over 4 is going to just be the reciprocal of tangent. Well, tangent was 1 over 1 for that 45-degree angle. The reciprocal of 1 is 1. In the second quadrant, where it's negative, it's going to be negative again. In the third quadrant, where it's positive, it's going to be positive again. And in the final quadrant, it's negative again. Okay, so we're going to take those points and we're going to translate them to our graph. We've got undefined at 0 and at pi. So that's going to translate to an asymptote. 0 and at pi. We've got it equaling 0 at pi over 2 and 3 pi over 2. We have it as positive 1 at pi over 4 and negative 1 at 3 pi over 4. Positive 1 at 5 pi over 4 and negative 1 at 7 pi over 4. Again, you'll see that this is going to look similar to, but not the same as, the tangent function. This is going to be decreasing as it moves, and the asymptotes have changed position slightly. They are still pi apart, so I'm going to just continue this pattern. They're still pi apart. We connect the dots. We should fit 4 full cotangent graphs in our pi or 4 pi window. So fill in those asymptotes at every pi. Your zeros should be right in between. You should go up to positive 1, down to negative 1, up to positive 1, down to negative 1. And those values, those dots should just be connected with your lines going toward those asymptotes. Okay, so basic properties again. Graph, or the general equation, is just going to be the cotangent of x. Domain again has some restrictions. This time they're at the intervals of pi, at 0 pi, at 1 pi, at 2 pi, at 3 pi, at 4 pi. So our domain is going to be all real numbers, except, we're going to use k again, except k pi, okay, no pi over 2 this time, just the regular pi, and it's for all integers, not just odds or even. So for all integers, k. Our range again goes from negative infinity to infinity. Continuity, because of those asymptotes, again we have no, it's infinite discontinuity. It again has symmetry with respect to the origin. If you rotate your paper 180 degrees around that origin, you should see that it looks exactly the same as it did originally. There are no min and max values because we're continuing to positive infinity and negative infinity. There are vertical asymptotes at every k pi. X equals k pi for integers k. What's the period of this function? Well, this is an easier one to look at. You've got an asymptote at 0 and an asymptote at pi. That has a total length of pi, just like tangent did. How is cotangent different from tangent? Well, the asymptotes are different. And, as I quickly mentioned, tangent is increasing on its domain. However, cotangent is decreasing on its domain. You'll see that as you go left to right, you're going down the whole time. Down, 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 down. Okay, now to get into actually graphing some of these functions. Okay, so we've got we're being asked to describe the transformations in terms of the basic function, locate all its vertical asymptotes, and actually graph it. We are not going to be asked about general properties like period and amplitude. There's no real amplitude to the tangent and cotangent graph, so that's not something we can really talk about. The properties work the same as they have with the regular sinusoids and with secant and cosecant. The 2 out front is going to cause a vertical stretch times 2. The 2 inside is going to cause a horizontal shrink times a half, because we take the reciprocal of b to come up with our stretch or shrink factor. So we're going to start off with our first transformation by vertically stretching it times 2. The easiest way to do these vertical stretches, the first thing you need to remember is that all of your asymptotes are going to stay exactly the same. So you've got asymptotes at all of those pi over 2, because if you stretch vertically, a vertical line isn't going to move anywhere. So start off by repeating your asymptotes. Your zeros are all going to remain the same as well. However, any place where you had a 1 value, so all those pi over 4s where it used to be a 1 or a negative 1 are now going to be a 2 or a negative 2. So you see that we are translating each one of those, or stretching each one of those points to either positive 2 or negative 2 before we try to connect the dots. So zeros stay the same, positive 1 becomes positive 2, negative 1 becomes negative 2, and then we connect those with a nice smooth curve. You'll see that it should look a lot steeper. That curve in the middle that we had on the original tangent graph should look much steeper now that I've stretched it vertically times 2. So hopefully you see that that steepness has changed pretty dramatically. Horizontal shrink times a half. Again, it's easiest to start in the middle. Anytime you've got asymptotes, it's going to be easier to move those things first. So our asymptote at negative pi over 2 is now going to move to negative pi over 4. Our asymptote at negative 3 pi over 2 is now going to move to negative 3 pi over 4. Once I get a couple of them, then I get the idea that they're going to be every pi over 2, but in the middle of each one. So I go ahead and I fill in all of my asymptotes. All my zeros are going to be right in the middle of those. My 0 at 0 stays at 0. My 0 at pi is now at pi over 2. My 0 at 2 pi is now at pi, and so on. So it's going to be every pi. Your vertical should stay the same, so it should still be going up to positive 2 or down to negative 2. So fill in those points. Those are going to be in the middle of each one of these. So you're using that halfway in between the 0 and the asymptote. Connect the dots, you should get a nice steep curve, and you should get a lot of them as you go across. Okay, on to example 3. Number 2 we will do together as practice tomorrow. On to example 3. You've got 1/2 tangent of negative x plus 2. Your first job is to identify what transformations you have. The 1/2 out front should cause a vertical shrink times 1/2. The negative inside the party is going to cause a reflection over the y-axis. And the plus 2 outside the party is going to cause your function to move up 2. Since we've got many transformations happening here, make sure that you are numbering them. Vertical shrink and reflection can go in any order you want, but I'm going to call vertical shrink number 1 and the reflection number 2, and I'm going to make sure that I know which transformation I'm doing as I go through my graphs. Now that I have all that down, I start with my basic tangent graph, which you'll see I already have graphed. Start off by the vertical shrink of 1/2. Any place where you had an asymptote, when you vertically stretch or shrink, is going to stay an asymptote. So translate those asymptotes back into the same places they started. Your zeros, any place you had a 0, your y value is 0. And 0 times 1/2 is still 0. So in the halfway spot of all of those asymptotes should be a 0. But now, where we used to go up to 1, we're now only going to go up to 1/2. Where we used to go down to -1, we're now only going to go down to -1/2. Okay, so that halfway point at all those pi over 4 for your domain, you're going to go up to now only 1/2 or down now to only -1/2. Connect those dots, and what you should see is that that middle curve line is now steeper, is now more flat than it was for your original function. Try to stay within the dots, connect those dots, nice and smooth curve to come up with your answer. Reflection over the y-axis. Well, your asymptotes, if you reflect, are going to end up in the exact same spot. The positive pi over 2 will end up at the negative pi over 2. The positive 3 pi over 2 will end up at the negative 3 pi over 2. So those asymptotes stay the same spot. Your zeros, if you reflect them, also end up staying in the same spot. But when you reflect those points at the pi over 4s, when you flip it over the y-axis, they're going to now cause this function to be decreasing instead of increasing. So translate all of those points and then connect them with a nice smooth curve. The final piece of the graph is to move up 2. If you've got a vertical asymptote and you move it up, it's going to stay in the same spot. So again, our vertical asymptotes stay in the same spots that they've been, at all those odd integers of pi over 2. Now our zeros get translated up 2. So now that whole, essentially what middle of our graph is going to now be centered on 2 instead of at 0. So I translate all my zeros up, and then each one of my points is pi over 4 left or right, and half up or down from where that 2 is. So you see, take each one of those points, translate it up 2, and then connect them with a nice smooth curve to get your final answer. Final example is example 4. Example 5 we'll do tomorrow for practice. Cotangent of negative 2x plus 2 pi. You've got a b value and a c value represented, which means that we have to factor before we can move on. So if you factor out the coefficient of x, that negative 2, you should get the cotangent of negative 2 times the quantity x minus pi, which is going to kind of change what these transformations are going to look like. The first transformation you should notice is a reflection over the y-axis that you get because of the negative inside the party. The second is due to the 2 for b. You get horizontal stretch or shrink by taking the reciprocal of b, which would be 1/2, which would cause a horizontal shrink. And the final piece of our puzzle should move this function right pi because of the minus pi. Again, since I've got multiple transformations, make sure that you're numbering these so that I know which graph you're doing as you're doing it. Reflections and shrinks can come in any order, those first 2. So you could have them flip-flopped if you want. I'm going to do them in the order I have numbered here. Start off with the reflection over the y-axis. The cotangent basic graph has all the asymptotes at the pi's. When I reflect over the y-axis, they're going to remain at the pi's. So my asymptotes remain the same. All of my zeros, when I try to reflect them, the 0 at pi over 2 will now be at negative pi over 2. The 0 at 3 pi over 2 will now be at negative 3 pi over 2. Again, they should stay the same. However, the difference here is going to be all the points that we had at our pi over 4s. All of those pi over 4 values, when we flip it, are now going to cause this graph to be increasing instead of decreasing. So connect those points and you should get your new graph. Horizontal shrink times a half comes next. Your asymptote at 0 should stay at 0. Your asymptote at pi is going to be moved to half of a pi. Your asymptote at 2 pi is going to move to 1 pi. Once you get the idea of what this will look like, you'll know that you have an asymptote at every pi over 2 value. It's going to give us 8 total pieces to this graph in our 4 pi width of our graph. Your zeros were at pi over 2, 3 pi over 2, 5 pi over 2. When you multiply, they're now going to be at every pi over 4. So I've got a 0 in the middle of each one of these asymptotes. It shouldn't change from increasing, so it should still be increasing, and you should still be getting up to 1 about halfway in between asymptote to asymptote, or 0 to asymptote. Down to negative 1, up to positive 1. Connect the dots with a nice smooth curve, and you'll get your transformed cotangent graph. Notice how in all of the graphs so far I've been drawing an arrow at both ends. That's to indicate that it keeps going up and it keeps going down. I'd appreciate it if you would do this as well so that we know where we're looking. With your pencil on a graph, it's sometimes also hard to tell where the asymptotes are, so make sure that you're extending the asymptotes past the actual graph so that I can tell that you've recognized where they are. And make sure that when you're sketching your graph, it's not passing any asymptotes. The final piece is to move right pi. Well, here our new period in this last graph that we've graphed is pi over 2. If I moved right pi, every one of those pieces should mirror every one of the other pieces, which means that what I'm going to get for my final graph is just the exact same thing as what I got for my third. After you repeat your final graph, you should be totally done.